first I have two very quick slides to say who we are, where we come from. So actually we came from the former group at Siemens and Infineon. And we have therefore also a very long background in formal technology. And we are now in the last years have been working to bring this worldwide to our customer base, not only in Europe but also in the US and Japan, for example. Okay, no problem. As I said, this stuff is anyway available, so you can look it up just to give you some idea of where we are. And well, we have kind of two main product lines. On the right-hand side, we have our equivalence checking, where we particularly focus on the FPGA side. So we work with all the major FPGA vendors there to make sure our equivalence checking really can cope with all the advanced optimizations in FPGA flows. And on the left and on the middle, you have the standard formal technology about linting and automatically generated checks, and also a quite comprehensive bunch of solutions, as we call them, Jasper calls them apps, and a lot also focus on coverage. But as I said, today I want to talk about a result that has actually been achieved by one of our customers, Renesas, and the rest of the presentation is actually based on what they have shown at the Verify conference in Japan this year. So if you have been there and speak Japanese, you might know the material already, but otherwise I hope it will be something quite interesting for you. So it's about the integration, SoC integration verification, where they found a lot of improvement potential in their flow. So the idea that a company like Renesas had here is, well, they have, like many of you guys, I guess, also have kind of a platform where they then spin out different products in this platform. They're just slightly different, but put in a different IP, add a couple of interfaces, or tweak with the parameters a little bit. So not changing the core components, but you have many very similar products. So a lot of reuse on the design side, and of course what you want to achieve is also to have a very high reuse then on the verification side, because otherwise this approach also does not scale very well. Now, to get an idea of the recombinations that are happening there, kind of we have the central components here like a CPU that are connected to a certain bus and peripheral bus, and then a lot of peripheral IPs that are plugged in then for the different products on the platform, and a couple of different external interfaces that you can also plug in, and also there are connections then via interrupts from the different interrupt sources from the IPs back to the CPU, and maybe also other targets who can handle interrupts. Now, what are then the challenges that Renesas has been facing then? On the one hand, of course, it's kind of the traditional thing, the obvious thing. You want to do a kind of reusable verification on your IP blocks, so the IPs are parameterized. So, of course, the verification has to be parameterized as well, because there's no way you can afford to do everything again for each and every different parameterized instantiation. But then also the second step is even the more challenging step here is actually also to leverage whatever has been done on the IP level later on for the SoC level integration verification. But we'll go into much more detail on that. So first thing Renesas has adopted when they took up our solutions was to say, okay, yeah, for our different IPs in our blocks and also for the platform modules, so platform are the modules that are kind of constant in the series, that they don't change from one product, from the different product in the family, just bunch them together with a couple of assertions, which is kind of the standard thing anybody would want to do once he adopts Forma, right? Add a couple of parameterized assertions for each of the blocks. And for that, leverage the usual advantages that you have in Formal. And one thing Renesas also found very useful there was to use an FVA library that we provide that allows you to write kind of easy assertions that kind of separate the cause and the effect in a kind of quite understandable fashion, and also give you an idea of defining time points. I cannot here really go into the details, but suffice it to say it's something that all our customers tell us it's for kind of new guys coming to it, it's much easier to use than all the intricacies of writing your own SVA and having to work with regular expressions and the strange semantics there and to worry about empty matches and whatnot. So of course, one of the advantages here is kind of writing these assertions kind of high level, transaction level, covering the interface behavior of the IP block, which of course is by construction covers quite a lot of ground because really it's transaction level and covering the whole interface behavior. Now, again, so where are we? Renesas bundled these assertions together with the different IPs in their library, and then for the different products in their platform, they plugged out the stuff again, and first of all connected the hardware parts then together to say, okay, this is our SOC, where they have the nice verification on the IP side, the assertions given, and now their question is about the integration side. So the particular application I'm focusing on here is just the interrupt functionality. So when you have plugged in everything here together, is it then really possible that an interrupt raised by the IPC, it really travels correctly to the CPU, one of the targets, and is then served there? And of course, that then goes through for all the interrupt sources of the IP and all the interrupt targets. Now, the problem here, of course, is when you think about it, there's then, because there are lots of components interacting, the amount of different combinations that you have to take into account becomes staggering here. Even if you just think of a simple system of 4 different IPs and kind of targeting for the moment just the IPC, it could still be the case that the others, they can have any behavior at this particular time. So could either reach no exception or one directly before the one from IPC at the same time or after. And yeah, it's basically then 2 to the or 3 to the power of the number of instances, different combinations that you can actually happen with these lots of different IPs. Now, what they did before they adopted our solutions was the traditional approach based on test benches. So for each then product in the platform family, develop a test bench and then have tests then for the different interrupt sources, trying to cover at least some simultaneously incoming interrupts also from other sources. Now, the problems they saw there is that the work there was not too reusable actually from one product in the platform to the next, because they had to set up the test bench, at least tweak it quite a lot for different products when there are different IPs in the system. So reusability actually left a lot to be desired on the verification side on this part for the integration verification. Now actually, when they adopted our product and saw this idea of writing these high-level assertions in this operational assertion style with this cause and effect separation, they got the idea that now what they can actually do is have a bunch of assertions for each of the IPs here and then use it as an input in order to actually create the complete integration verification based on these existing assertions that you have from the IP blocks. To give you a little more concrete idea, so again, the example is just the interrupt system, but they also apply this in general to a bus connection matrix where bus masters and slaves talk to each other, so also with addresses and data and not just the control part that you have for interrupts. So there's a bunch of assertions associated with the IP that talks about raising the request. They have assertions talking about routing the request from the source to the desired target and then about the request being served. And these are then kind of recombined to a big SOC integration assertion. So taking the cause from the originating IP that creates the interrupt, taking something from the interconnect part, and finally checking that actually, yes, it arrives in the target and it's correctly served. So in this way, by just pulling out the stuff that they have in their in the IP databases assertion-wise anyway, and creating this one assertion, they actually get to the system level integration verification. One concrete example that kind of gives you a little bit of an idea. So it talks about a pulse happening on an interrupt signal, and this signal in some way being routed in the interconnect, and then actually at the receiving end, at the target one, it's actually then sampled, and also the interrupt level is set appropriately. And basically this assertion, they then throw at our tool and actually run it then on the system. And this is actually the numbers they presented also then at the Verify conference, really just to compare. So in the first column here you have the simulation. So we have 547 different interrupt sources in the particular system where they did really a heads-to-heads comparison. Over 100,000 lines of code were developed for test bench and test cases. Of course, some of that was automated, but still it was 2 person months of effort to do that. On the formal side, it's actually here are 2 columns. The first is just developing the assertion on the IP side. These 547 assertions. It was kind of a 1-week effort. And of course, this 1 week is not a full verification of the IPs. It's just the interrupt functionality, nothing else of the IPs. Otherwise, of course, the number would be not really realistic. And then checking these assertions on the IP, it's a pretty quick task, 9 hours. And actually then checking this combined system level integration assertion that for the concrete system checks whether one of the interrupts under any possible circumstances will be served on the other side by the CPU is also something that where our tool scales very well, and in a runtime of 3 days gives them the answer. So as you can see from the numbers, it's basically a saving of an order of magnitude that Renesas has reported on this. So let me sum up. So by using formal here on the IP side, on the one hand they got the high coverage anyway that you get from the formal side of the verification and compared to the simulation. And of course, by just doing it parameterized, the assertions, they had the reuse, the appropriate reuse, but also the additional benefit that they did not have before in their simulation-based flow was that they really can reuse the assertion exactly as is for their system integration verification. And it's kind of obvious why they came up with this flow, because it saved them an order of magnitude of effort. In addition, also created a higher verification quality. And that sums up what I wanted to report from, kind of a customer presentation, but at least the results are concrete customer data.
Very interesting. Thank you very much.